I'm Xiaowen Chen. I'm from University of Chicago. And Megan, where did she go? Megan Donahue from Michigan State University, and I have been asked by the conference organizers to lead the discussion session now. So I thought, coming from, we have heard many wonderful theory talks so far. So I thought what we could do is to just tie that to observations, just trying to provide some observational perspective. So I thought just follow the quote that Alex mentioned from Frank Shu. I thought that statement may be somewhat incomplete. Once the simulation can produce perfect results like Crab nebulae, you need to develop a theory, formulate a theory for that. And I thought the next step would really be to test the theory with additional observations. And I hope this is what the session, the purpose of this section will serve. So, but then, it's just to frame the discussion, what we would like to do is, coming from observational standpoint, what kind of implications on specifically turbulence and pressure support, there is Megan, on the circumgalactic medium and the intra-cluster medium. So now just to, what just happened? I don't know what happened. Just to frame everything, I understand that, it's probably mostly about semantics, but while we can say circumgalactic medium and intercluster medium are the same, but I think, given the parameter space we probe and each, the target we observe, there are fundamental differences that mostly are driven by the observational techniques. So I want to start with this table just to define frame what we are going to focus on in the next hour or so. So when we talk about circumgalactic medium, really we are focusing on, primarily driven by observations on single galaxy halos on the order of, in terms of dark matter halo mass, we'll be talking about anything less than of order magnitude 10 to the 12th solar mass. And then for ICM, it really is driven, focusing on really massive galaxy cluster halos. And by massive, I mean up to 10 to the 15 solar masses. And given the different mass scale, you can see that the temperature range is really very different. So far what we have learned from observation is the circumgalactic medium is mostly multi-phase. We can broadly define, separate it into 3 different phases, but I'm not saying it's just 3. It's really more like a continuous spectrum. But roughly speaking, we can separate that into cool phase, 10 to the 4 Kelvin, to somewhere in between warm hot phase, 10 to the 5 to 6. I'm picturing the cooling curve. And then into the hot phase, even the hot phase regime, we're talking about 1 million degree Kelvin. That's not quite into the X-ray plasma that you have been hearing about. And that presents the fundamental difficulty when it comes time to study the multi-phase medium. And, on the other side, for the massive halo, we're talking about, 10 million, 100 million degree Kelvin gas, booming in X-ray. So there are abundant X-ray data just by surface brightness fluctuation or even just line width. You can put a lot of constraint on different observables that that's on starting from temperature to gas density to metallicity. We have heard a lot about velocity fluctuation. We can do that both in the low mass CGM and also in cluster environment using different techniques. And it was really in the last minute I realized I need to add magnetic field. But in the CGM, it's really a big question mark. Maybe I should have said it's non-zero. That much we know, but exactly how much we don't know. In the ICM environment, I guess order of magnitude speaking, microgauss. And just, on the right, you can see this mass composition for different types of halos. In terms of multi-phase, again, voltage 10 to the 12 solar mass halo, we know, roughly speaking, hot gas is still dominant, even though it's not as, completely driven, the mass budget in the cluster halo mass. But it's still, we could be talking about 60% of the mass lies in the hot phase. But there's a significant contribution from the cool and warm hot phase as well. And they play a significant role in, even just beyond the plasma physics. It really is tied directly into the galaxy formation and evolution. So I want to, orient everybody with these charts.
That's good. You have velocity dispersion variance of sonic subsonic. What is that? What is that in terms of like Mach number?
I will come to that.
Okay.
But Mach number is really, less than 1. But there are a few cases we see, over 1 to 2, but it's not like 10. Yeah. All right. So moving on, I'm just gonna, yes.
Difference between the filled bars versus empty
right,
bars?
So that's the solid, thank you for the question. The solid bars are what we see. So it's a lower limit. The open hashed bar sets the upper limit based on our educated estimate. Right. All right, thank you. So moving on, I'm just gonna go over the techniques we use to come up with these numbers I mentioned here, and then I will transition to Megan to talk about ICM, and then we'll close with the number of questions. So just to start out, what I do, a big part of what I do is absorption line spectroscopy. We sort of talked about that in Matteo's talk yesterday. The idea is, this is pencil beam survey of background light shining through space, intercepting any gaseous clouds through density, and it will imprint absorption features. And through the utility of high spectral resolution, we can resolve the gas into multiple components. Here, I'm just highlighting one system that has 2 very clearly resolved components that shows many different transitions, starting from hydrogen Lemoine series in the top 2 panel that you see. This is the velocity profile, followed by 2 low ionization species by carbon and nitrogen associated with the hydrogen gas that we see, followed by high ions, oxygen 6. This is 5 times ionized oxygen. It requires a very energetic photons or very hot electrons to produce this kind of species. Well, one thing I want to highlight is, I hope it's clear to you that even for the same gas, 2 different components, the relative line strength are different between the 2 components. Immediately, just doing the back of the envelope ionization correction, you can see that it tells us the ionization fraction is very different. One thing, this component highlighted in orange is highly ionized because it shows very strong oxygen 6, whereas the other one shows no oxygen 6, low ions. So this is the power we have that can help us constrain the density fluctuation. And on the left, that's the cartoon that shows how we can make sense of this kind of fluctuation by doing this kind of deep projection, because each psi line runs through the entire halo, runs through a range of radii throughout the halo. One possibility, which is our favorite scenario, is the high ionized species lead to low density. And that occurs primarily, most likely in the outskirts of the halo, if you assume this density profile, which is also, guided by the pressure profile that people see in X-ray in nearby galaxies. And the high density, low ionization component will come out of the inner halo. And in addition to that, we can also see, now this is an expanded version of another system that has more than 2 components detected. So this is the painstaking, very careful, exercise to decompose what seems like a single absorber into multiple components based on the line profile, based on the high spectral resolution. And what what I want you to focus on is this highlighted component on the left. You know, this is at about -60 kilometers per second relative to along the line of sight. And again, this is covering from low ions on the left to high ions on the right. This is a very clear example, even when all the ions are lined up very nicely in the velocity space, they don't necessarily come out of a single phase. And this is what's shown in the ionization model. Comparison between model and the data shows. A single model shown in blue, that's highlighted using the low ions. Again, this is kinematically matched absorption signal. And it turns out that we require at least two phases. You know, there's a high density phase and a low density phase. This is a clear empirical piece of evidence that shows the presence of multi-phase gas. Just by looking at the kinematic alignment coupled with the relative strength between different ionization species. So, I forgot to mention that I gave an hour-long discussion last week at the workshop. So I'm not going to repeat everything I said there. I would just encourage you, if you're interested or have a question about the techniques we use, please check out the slides online or the video. So going back to this picture, now we have assembled a sample of this intervening halos probed by a background sideline. So now you can see that in this particular paper, we put together a sample of 20 star-forming galaxies at redshift 1. And for every single sideline, this is led by a postdoc, Zhijie Chu at Chicago. He did a painstaking job to decompose these components and did the ionization modeling and infer the density for each component. And you can see that it really, along each single sideline, the density fluctuation goes beyond an order of magnitude. It's really dramatic. And so what does that mean? You know, there's really the question about pressure support. And this is indeed a really information loaded figure. So you've seen this yesterday, but if you look at the data points, this is what we measure component by component, you know, along individual sidelines. And despite the large scatter, you can see there's a general declining trend from the inner halo to the outskirt. So that supports the idea of the deprojection of putting the high density in the inner halo with the low density clumps in the outskirt. And it shows when we do that, compared with the density inferred from hot halos, this is based on stacking of Sunyazev-Lovich maps coupled with the X-ray maps of, you know, a million Sloan galaxies. If you look at the comparison of the hot gas density relative to the clump density, if we just do a very naive binary model, raise the density by a factor of 100 with the expectation of the temperature ratio by a factor of 100, you know, a million as opposed to 10,000. That's what you will see in the dashed line relative to the best fit of the upper envelope highlighted by the blue circle. It looks to be quite a nice agreement to winning the uncertainty, but granted, there's a huge scatter. So because there's a range, we also plotted the 1,000-time upward scaled density profile to show that to encompass the range of halos we looked at in this sample. This just goes back to the difficulty. While we can do we can do our best to constrain to reveal the density fluctuation and everything else, we're still limited by the sample size. There's inherent, you know, we're talking about, after all, astrophysics gas. It's really messy and complicated. So the scatters here, we really need to increase the sample to really say something for sure. But while this is order of magnitude speaking consistent with pressure equilibrium between the presumed hot medium and the cool clumps, that by no means rule out the need of non-pressure support, non-thermal pressure support here. But I just want to highlight the contrast, over the decade. Significant amount has been learned over the last decade. That shows that, when we really utilize all the information the data has to offer, we just see our view gets so much better. This is the early result from a decade ago from the Cos Halos team that shows that the cool clumps, the best gas density come out to be on the same level as the hot medium, and that's really that's really due to the fact that the resolved clumps weren't utilized in the ionization modeling. This is really the updated result. But what all that says is non-thermal pressure support. It's still not ruled out, but it's just not order of magnitude. The kind of expectation from 10 years ago. So in addition to just one more slide on the pressure ionization model, another independent information we can use really is also the line profile. The line width, everybody appreciates that the width gives you measurement of velocity dispersion along the line of sight, in this case within each single component, each single clump. And when we compare the line width of the same clump, but using different lines from different atoms, different particles, different elements, we can also hope to decompose the contribution from thermal and as opposed to non-thermal motions. And this is what we have been doing since 2019. And when we do that, we get independent estimate of the temperature that's not relying on any ionization model assumption. So we can use the temperature derived from the line profile and the density inferred from the ionization model to check our assumption in the ionization modeling. In this case, it's for ionization equilibrium. So again, in the data is really, there's a lot of scatter. The green band here shows the best fit relation between temperature and density. So to the 0th order is, it's comforting to see that the full ionization model isn't such a egregious assumption. So so that's what we do to get the density and temperature fluctuation. So now in terms of pressure support, that's what I would like to cover in the CGM. Before I move on to talking about turbulence, any questions? So then I'm gonna move on to talk about turbulence. Using the same technique, just want to focus your attention on the left panel here. When we infer the density. Yes.
How many slides approximately do you have? So we have time for discussion.
So I have 2 more slides plus Megan's.
Maybe quickly wrap up in the next couple minutes so that we have time, like half an hour for discussion.
Okay. So going to talking about turbulence, using the same ionization models, we can infer the size of the clump given the density and the expected ionization fraction. And that's shown in the left panel here. And we can look at the general overall distribution. There's sort of an anti-correlation trend that's set by a fixed constant total gas column density. And there's some interesting physics that goes into that. If you're interested, we can discuss that later. But using the size information, we can look at the velocity size relation. So this is the power of absorption line that allows us to resolve clumps down to 1 parsec scale. And going over to 1 kpc, if I just consider the 3 orders of magnitude range, we get a very nice slope that follows 1/3 within the 3-decade dynamic range. That gives us the inferred energy transfer rate comparable to what people see at high redshift. And the size here is very much comparable to what people see in 21 centimeter survey in the Milky Way halo as well. So I'm just gonna move quickly into a complementary way to constrain turbulence in the CGM. Now that we have really powerful integral field unit spectrograph that allows us to reveal line-emitting nebulae around luminous galaxies. In this example, you can see in the top panel is a galaxy group at redshift 0.3 that does not have any quasar or AGN found, and there's the giant nebulae found around it that spend nearly 100 kpc. In contrast, the bottom panel shows a quasar host halo. And with this velocity map, we attempted to measure velocity structure function. What you see here is both the second and third order velocity structure function between left and right. And it shows, you know, a really nice Kolmogorov slope that's also not quite expected to win the uncertainty. Similarly, for the quasar host halo, we also see a very nice Kolmogorov relation. So this is, again, there are many systematics when it comes to observational techniques. What you see here just address two of those. One is the PFS smoothing. That's why the power law seems to be curved. And another one is bulk flow contamination that adds the power to the velocity structure function measurement. But this is what we have attempted to remove these factors and still we recover Kolmogorov relation. So this is just a summary of what we know so far in diffuse gas content over many decades in spatial scale. What kind of turbulent heating that we can determine constrained from empirical data. So I should move on to hand this over to Megan to talk about ICM.
So we're, as Xiaowen mentioned, when we're talking about clusters of galaxies, we're talking about the hot phase, a hot volume filling phase. As an X-ray astronomer, I can tell you, I have not spent much of my career thinking much about turbulence at all. And so I came to this meeting in the hopes of like getting a crash course in turbulence in a way. Because turbulence is something we are just now starting to say anything about, except, you know, very indirectly in X-rays. So one of the questions I'm going to pose to you at the end of all this is what sorts of observations or things should we be trying to look at in X-ray and UV observations in the sense of how can we improve our science justifications to improve our science? And this also might improve your scientific justifications if you're connecting to, you know, the broader science of feedback, galaxy formation, and so forth. So this is a mutual exchange of ideas here, my first set of pictures, though, is just showing the plethora of morphologies that we've been, you know, dealing with in X-ray astronomy and observations of clusters of galaxies, from, you know, merging clusters with irregular distributions of gas surface brightness fluctuations and high temperatures in the center and things like that, coupled with radio observations of radio halos, radio relics, but rarely radio sources in the center, to relatively relaxed clusters, not perfectly relaxed, but relatively relaxed clusters where everything's sort of nicely peaked, single peak X-ray sources. Some of them are very strongly peaked. These are known as cool core clusters, and some of them have a little more diffuse, flatter central surface brightnesses. And, you know, so I have two exemplars side by side from Chandra. And so clearly the merging clusters, folks who study plasma physics are you know, have been talking for many decades about, you know, wave interactions and particle simulations of the diffuse regime around merging clusters. I'm not here to talk to you about that. What I'd like is to draw your attention to the more relaxed clusters, where we still, to explain what's going on in relaxed clusters, need to invoke turbulence and turbulent dissipation to explain how, for example, the energy of AGN feedback gets shared with the rest of the plasma. And so this regulation seems to be extremely important in explaining how massive galaxies and massive clusters evolve. Oh, yeah.
I would like to, I'm under the impression that during mergers, the magnetic field strength is expected to increase, and therefore we would expect the radio emission to be enhanced in the upper images compared to the lower images. Is that a correct expectation?
You do expect the magnetic fields to, I mean, they are measurable, but they're measurable in both. There is measurable rotation measure from the radio sources in the centers of these cool core clusters. And so the difference is morphology, huge differences in morphology. The halos in the mergers are diffuse. They're not necessarily centered on the BCG, whereas the radio galaxy emissions.
So there is actually no difference in the actual strength of the synchrotron emission. Is that right?
Might be asking the wrong person. But the radio synchrotron AGN luminosity can be like 10 to the 24 watts per burst.
You typically get giant radio halos in mergers.
Yeah, but they're rare. You need a big merger to get a radio halo.
I mean, I'm asking because people like Jim Stone, for example, produced models of magnetic field generation from merging clusters. But that was quite some time ago.
Right. So
Do you have?
If I can beg for
would you
your
have any
time-
comments on this? I mean, are you out of that business in the meantime?
That was an old paper. That been many such studies since, and so I have no comment. No.
Right. Yeah. If I could draw your attention to the relaxed clusters so we can talk about what I know something a bit about. And then we can, in the discussion, we can broaden to, the messes known as the merging clusters. Okay?
Megan,
So,
can you explain the color scheme?
What's
Can you
that?
explain the color scheme?
Oh, the color scheme is purple for X-rays, of course, blue for, up there, it's blue for where the weak lensing mass measurements are. Okay. And here it is orange, and this is just an X-ray image over here on the side. So one of the things I wanted to point out with this X-ray image is you're looking right down into the core in the central 10 to 100 kiloparsecs, and you do see interactions between the radio plasma and the X-ray plasmas that have allowed us to get a bolometric estimate for the actual energy output of radio sources, which was something that was almost impossible to estimate just from the radio alone. And so the kinetic energy that's being dumped into the X-ray emitting plasma is enough to compensate for the cooling of the plasma. But if you go to if you go to lower mass systems with, similarly strong radio sources, that radio energy, that radio source energy, more than compensates for the cooling luminosity. And myself, Mark Voigt, but also groups, for example, Sandy Faber, have pointed out that the amount of energy that seems to be required to quench these central galaxies is enough to, is comparable to the binding energy of the system. Not just the cooling energy, but the binding energy of the system. So this energy is somehow getting dumped into the plasma and lifting it, reducing its density. And how does this happen? Presumably the thermalization of turbulence. I'll also draw your attention to, even when relaxed galaxies, we see central galaxies that are on lots of multi-phase gas, a radio central galaxy that's probably fueled by cold gas condensing out of the intercluster medium. And then we also see galaxies where there's no radio source, there's no multi-phase gas. And the main difference between these two situations is the thermodynamic state of the hot gas in the center of the cluster. In these clusters, there's low central gas entropy, short cooling time in the gas. And in these clusters, the cooling time is long, longer than about 1 billion years, and the entropy is higher. So I was going to point out that, if you talk to X-ray astronomers in the last 20 years, there's the evidence for pressure support coming from turbulence in the ICM is relatively low. There is gas pressure that compensates for the gravitational support of the gravitational pull on the gas, and the need to invoke other pressures, including turbulence, is minimal, especially in relaxed systems, and that is based on comparisons of mass estimates from hydrostatic estimates assuming only gas pressure compared to that in weak lensing. All right. Some other thoughts about multi-phase gas and turbulence and how they're related. Peng has thought about this quite a bit, but it's possible that the presence of multi-phase gas in the center of a cluster requires some turbulence in the ICM, even if it's not so important in supporting the pressure against gravity. And that is when the cooling time is short compared to other time scales in the gas, like dissipation, these condensations can form. If the cooling time is long compared to this dissipation time scale, you'd expect single phase plasma, no condensations, and actually relatively low turbulent support as well. So there is a system that's kind of puzzling in this whole picture of BCGs that are on versus BCGs that are off. Is Abel 2029. It's in the early observations of CRISM. I don't know what the observations are showing, but the reason for Abel 2029 being in that list, I think, is because it has extremely low central cooling time. It has an extremely peaked surface brightness profile, yet it has no multi-phase gas. It's been searched very hard for molecular gas, and for H-alpha, it has neither of those things. And our prediction is that it's going to turn out to be really quiescent, like low turbulence. The lines will be relatively narrow compared to the velocity dispersion of its enormous BCG. The velocity dispersion of the BCG is about 400 kilometers per second. So it's one massive galaxy. So this is my last set of slides, and it's pitched at questions to you. What are the most important observations we could do as X-ray astronomers, as UV astronomers of the CGM and the ICM? On the horizon, Irina gave us a little taste of what's coming from CRISM. We're able to observe this hot gas volume filling phase of clusters. Remember, it is optically thin. We're seeing everything along the line of sight. So any velocity dispersion we measure along that line of sight is by its nature an upper limit to the actual turbulence that's in the gas. And it's weighted by the density squared. So we may be able to sort out things that are centrally condensed more easily than something that's spread out over the sky. So they are observing merging clusters, but those I think those observations will be harder to interpret. UV absorption line spectroscopy has sort of been limited by the size of Hubble. So the next generation of UV telescopes will be bigger. We'll be able to use more background sources. That means better sampling of these gas halos along the line of sight. There's been some really interesting stuff in the cold gas and the filament systems coming from AMA. Will be coming from JWST, from the IFU in the south, from Muse, from Sitel on Mauna Kea. One big question is this a cheap way of measuring the motion in the volume filling phase? Are the gas motions in the cold phase tracing the volume filling phase? And what are we learning, even if that's not 100% true? And so just to open the discussion section, what are these compelling science cases that connect the physics of turbulence to other areas of astronomy? I just got in my email like 1 or 2 days ago an invitation to think up a 3 million second observation observing one cluster with Chandra. What could you guys do with that? Right? I mean, it's an interesting question to pose to a workshop like this, where we have all these people together caring about turbulence. How do we get attacked to care about turbulence and say, oh, that cluster that you guys want to look at, let's look at that one, and let's get that 3 megaseconds. So it's timely. So what do you think?
I really enjoyed the review talk by Xiwen, and I only want to disagree with one of your first statements, and this was related to Frank Schuh. Frank Schuh did not need the observations, because he was thinking that you get everything for the Crab Nebula already in your computer. You don't need any observations after that. And you just analyze, and that's it. And related to the talk by Megan, I would say that a very important issue was raised there. And this issue is related how to get from observational data the information of turbulence. And in the case of the interstellar media, we had this problem. And for many years, the relation between the velocity space, PPV cubes, which people were using, and the turbulence was pretty obscure, because we know that both density and velocity are contributing to the fluctuations of these PPV cubes. And you have this integration along the line of sight, all those complications that you correctly pointed out in your talk. And the word is channel maps. They were analyzed, and people were trying to relate directly what they saw, the slope of in these channel maps, directly to the underlying turbulence, which was wrong, because we know this phase space and real space are very different. And actually, Susan raised a very important question of how to get the turbulence if you have information in the channel maps. Some time ago, actually, not 100 years ago, but 25 nearly years ago, with Dmitry Pogossian, we addressed this mapping of velocities and density into the phase space, and we obtained the formula. It was done only for one phase media. And it was a very important question that Susan is worried. What is happening in two-phase media? Fortunately, for example, in our case, we managed to get high-resolution two-phase H1 simulations, and we tested this. I think we obtained the results that we expected from our theory. And in your case, I think the same should be done. There should be a very, analysis. No, I'm not giving another talk.
So I can hardly wait to have this argument in X-rays because we've been waiting for the spectroscopy, this kind of spectroscopy for decades, right? And so our first view is going to be of low resolution, low angular resolution maps of the sky. Something like the line emission mapper will be able to get a map of the emission, like oxygen 8 emission line across the entire sky. Very exciting. Sorting it out will, I hope, be somebody else's problem. I'm very excited to just get my hands on that kind of data. But certainly sorting out our Milky Way will be tough. It'll be, I think, a little easier to sort out or less more distant objects where we can see everything and see multi-phases with the different different velocities and so forth. Yeah.
Okay. So I wanted to address your third question here. The filament systems presumably consist of condensed gas from the hot phase, presumably. And if so, that gas is going to bring its additive momentum together. And so will probably not reflect the hot phase motions because those momentum will cancel. And when you go from low density to high density and you are conserving momentum, your velocity has to drop.
Right. So I think that will be an effect for the molecular gas, which has to condense quite a bit. But the large-scale filaments aren't really making disks yet. There's
No, but I don't think you need to make a disk to still see this, because I see this in molecular clouds, or not molecular clouds, but dense clouds in a supernova-driven ISM, where you've got a hot rarefied phase at high velocity dispersion, and then the clouds are down by a factor of 100 in velocity dispersion because their density went up. And I think that's going to probably be true in any, enhanced density.
Well, if the velocity dispersion is up by a factor of 100, we'll definitely be able to see it in the broadening.
That will be
and then Perseus, the one example we have so far, doesn't show that. And in a comparison between the H-alpha filaments in Perseus in the same region, gives a similar velocity dispersion in the H-alpha filament gas. I mean, this is multiple filaments to define a dispersion, but in that same region that's probed by Hitomi, they also see a comparable velocity dispersion on the filament. So I don't think it's as extreme as that, because they both see about 160 kilometers per second. I would not be surprised if AMA measured CO to show different velocity properties. Yeah, no, it's.
So I can comment on that. So Irina and I actually compared our results, right? So when we looked at the kinematics of H-alpha, Irina actually cut out a region in the X-ray map that matches where the filaments are, and Irina's analysis perfectly matches the H-alpha kinematics, just right, more or less, within the scales they cover together, while the X-ray doesn't go down to smaller scales. And in another system that I don't remember the phone number of, but you do, about blah, blah, blah.
2597?
There's definitely a 9 there. It's in my paper. So we do have ALMA data and Muse data of the H-alpha filaments. And the structure functions are more or less just sitting on top of each other. So even the molecular gas is moving together with everything else, it seems. Believe it or not, that's what the data says. But I have another question for both you and Xiaowen. Sorry, just a really naive, serious question. So Xiaowen, you talk a lot about this absorption line analysis. It's so beautiful. And I vaguely remember a paper by Mary Putman looking at absorptions in the ICM, I think for Virgo. Is there any follow-up on that? Have people tried to probe the ICM in absorption?
Right. I was on that project as well. It's a hard project. So we only had constraint on using hydrogen lemma alpha line. So the main point is to map trying to identify warm hot gas out of otherwise hot X-ray plasma. And turns out we found very little in the central core within the central visual radius. But then it starts, the detection rate starts to rise as we go to the outskirts. But Virgo, as you know, is also a very complicated cluster. It's just in the process of forming. There are a lot of influencing groups. So it's really hard to interpret that particular data set.
So is there more data on better clusters?
There's a second cluster that is coma, but then the number of probes decreases and it is hotter. So those are the two clusters for you. So we'll just go back to the second bullet point that Megan mentioned. We need to look into the future, and we need support for that kind of facility.
Yeah, that's the politics behind this question. Is we need support for sort of the Astro 2020 recommendations, because these are the missions that will do this UV science, that will do the X-ray science, and right now there's not much will, especially at the NSF for doing, the large recommendations from Astro 2020. So I know you're all theorists, but we're all in this together. So any support you can give is going to be appreciated.
Thank you.
Chris, next.
Thanks. To add to your list of facilities, of course, we should put Athena, the Athena Observatory, which is now back in the ESA plan. Sorry, I thought it was on the microphone. I say to add to your facilities, we should add Athena, which is back in the plan, and will be able to start to actually map out the spatial scales that are very relevant for the driving of the turbulence. And so, along those lines, the sort of question I had is, if you look at a system like Perseus, where everything is beautifully laid out on the sky, and there's a lot of, we can see, presumably, the different driving sources. We can see the bubbles being blown by the jets. We can see what we think are sloshing modes. Right. We can sort of look further out. Is there now a possibility for actually digging into this multi-scale driving problem, actually seeing the different nature of turbulence behind the rising bubbles versus in the sloshing modes, and what ultimately will we learn from that?
If the theorists can tell me exactly what those signatures are, I can tell you whether the observations might have a hope of seeing them. That would be my turning it around and saying what would be the especially the spectroscopic signatures of those things. And we see edges and things like that with the exquisite 900 kilosecond Chandra maps of Perseus. So adding spectroscopy to that, what added value does that bring, and what would be the signatures of these various types of energy injection?
Irina, were you going to say something still on the X-rays? Because I was going in a totally different direction. No, for Irina.
Well, it's more like a theoretical question related to what people said before. One of the questions we really need to think about how we distinguish genuine turbulence from all the rest. All right, we are interpreting all the complex dynamics following Kolmogorov theory, whatever. It's great, but it's wrong, and we all know that. So that's a question for observers and theorists in this room to really think hard about it and how we can decompose. There are some works trying to do that, but there are problems. This is not the answer. First steps, but I would encourage people to think more about it.
So I had a very broad question in a completely different direction, which is about dust, because it's always struck me that dust in the ICM and CGM is a particularly important probe of the multi-phase gas dynamics, given that it's destroyed so quickly in the hot gas, and given that it's produced so abundantly in AGB stars. So I guess the broad question is, what do you think we have learned from the observations of dust in the ICM filaments, dust in galactic winds in the CGM, and are there other avenues there that could be pushed to really sharpen our understanding of the multi-phase gas dynamics?
Dust is its whole puzzle. I think dust in the Milky Way is also a puzzle. But just to talk about the ICM, and I'll hand over to Shaun, that the filaments are clearly dusty. It's possible that some filaments are not dusty. I was looking at some spectroscopic evidence where Valeria, she can show you pictures of, okay, she won't. But it's a poster, okay. But for the most part, these emission line filaments are dusty, and they have things like PAHs in them in addition to dust. So really fragile dust on top. It's not just dust.
But the dust should also be everywhere because there are AGB stars filling the entire, halo.
Right.
So is it that they're just not, the dust is just not being irradiated enough that we can see it?
There's So there's very limited evidence for, like, for example, infrared emission from dust from the smooth ICM. When we look at these systems in the far infrared, the filaments glow. Mm-hmm. But the ICM, as far as we can tell, does not. So there's not much evidence in reddening, searches for reddening, through, when you look at background galaxies and you compare colors through clusters, there's not a ton of evidence for dust in the ICM. But in the filaments, it's there for sure. So the connection between the two becomes, how if these are really condensing, right? Where are they getting their dust from? And the AGB stars might be making it. It might be pulled out and seeding the formation of more dust, but that's more of a dust question, I think.
So we may move to the next question.
Wait, just quickly.
Because there are
we do see dust in the CGM. We do have the signal there, but it's hard but the signal is really weak. It's really, if you just look at the satellites that contain strong absorbers, just look at the background quasar colors relative to the satellites that are empty, transparent satellites. The quasars tend to be redder, but the signal we're talking about there is like 0.2 magnitudes, but it's detected. And we can also look at the elemental abundance pattern. There is depletion, but that's also more complicated because it also is coupled with the enrichment source. So we have to get the fundamental enrichment pattern settled first before we can actually constrain dust. All we can say is it looks as though dust can survive in an otherwise harsh environment. That's really not well understood. Right.
And we do see it being ejected in like M82 and NGC 253s.
Mm-hmm. Yeah.
Yep. Yeah, we have a few more questions.
Thank you for the
I'm sorry, just one suggestion. We have 3 people and 5 minutes. So in the interest of everybody getting a chance to speak, let's try to keep each question answer session to like a minute and a little bit.
Okay, I would discuss a couple of points, but maybe I'll just say one. Okay, so thanks for the great discussion. So one point that, I'll make 2 quick points. So first one is when we are talking about velocity structure functions in a non-volume filling medium, then the effect of projection is very non-trivial to understand. So if we are just looking at the hot phase and it doesn't have that many density variations, when you're projecting it, you expect some cancellation and the structure function will steepen. But if you're talking about a non-volume filling medium, then the cancellation effect is very strange. I mean, we didn't even understand it properly from our idealized simulation. So that is something to keep in mind. Second point was when we are comparing between the X-ray measured surface brightness fluctuations and the H-alpha, just yesterday, we had a talk in which we are seeing that the X-ray surface brightness is enhanced near this H-alpha emitting filaments, right? So, which is also something we see in the simulations that, the dense regions where we see cold gas, the density fluctuations in the hot gas is enhanced simply because you have converging flows trying to going to this cold gas. There's also mixing between the cold and hot medium, so the density fluctuations will be enhanced in those regions, which may not be due to turbulence only in those regions. So we just should exercise caution when you are, looking at density fluctuations around those cold filaments and trying to measure velocity.
Yes.
That was short.
Yes.
Alex.
A very simple point related to Irina's comment. Indeed, the intercluster media is multi-phase, very complicated, and we have many effects. However, in the interstellar media, we already passed through this. We developed a number of techniques, and I think it should be more synergy between what has been done in the interstellar media, which is even more complicated compared to the intercluster media. So that's, I think, a very good place for such a discussion.
Maybe a reading list for X-ray astronomers.
Just a very quick point about Elliot's question about the dust. So you can take just a standard wind tunnel and put a passive scalar, which has density and temperature dependent dust sputtering. And it turns out you can accelerate the gas and preserve the dust, primarily because when you mix the gas temperature still tends to peak at 10 to the 4 K, where dust sputtering is very weak. So you know, we just run so Zurei Chen, who he's not here, but he's a young graduate student who's run these simulations, and at least at face value, you might think molecular gas is the stone, which is, you know, 100,000 times denser than the coronal gas, but it's really because during the acceleration process, the mixed gas tends to be at photoionization temperatures. So that tends to help. Of course, it's idealized simulation with all the caveats. Yeah.
Not from cooling. I think that would be the implication.
I was there when you had that epic debate with Andy Fabian.
Epic.
So with that, I think the session is concluded, and now we have lunch. And do we have other announcement?
So the announcement is that we are back here at 2 p.m. and we will have the exciting discussion on the heliosphere physics.